In this lab, we will continue with the tree and ensemble methods. So what we did in the we fitted the random forest model on all the predictors, and we found that uh, the uh, out of bag estimate of error rate was higher, um, of 0.1723. Then we fitted the random forest on square root of the number of that was 7. Send up 7 randomly chosen predictors, and the out of bag error rate was the out of bag error rate was uh, we had 0.123 for fitting all the predictors for the random forest model, and for uh, fitting 7 randomly chosen predictors on the random forest model. The out of bag estimate of error rate is 0.1591%, 0.1591, which is a bit less. So now, and the test error was approximately same for both fitting all the predictors and fitting the square root of number of predictors. So now in this lab, we look at the boosting method. In the following lab, we produce a boosting model with 500 trees constructed. We use a Bernoulli distribution by converting the two class vector values to 0 and 1. We use the training set. So use distribution equal Bernoulli for a two class classification problem. Let train 2 equal to Columbine of train, and class 2 equal has dot integer of train at class minus 1. So has dot integer of train at class will give us 1 and 2, and when we minus 1, that will give 0 and 1. So we get this. So train is binded to has integer of train at class but minus 1. So we can see that the train and class is in factor form, and has integer, it will be either 2 or 1, and subtracting 1 from there will be 1 or 0. From the results, there were 41 predictors, of which 35 had non-zero influence. Let's look at that. Fit the boosting model. Interaction depth between 1 and 5 is sufficient. Let R2 equal gradient boosting method, that's GBM, of class 2 fitted to all the features but not class, because class is the has part of the response variable. Data equal train 2. So data is train 2, which is the combination, the Columbine of train and the class column has integer minus 1. Distribution equal Bernoulli. Number of trees, which is n dot trees, equal 500, comma, interaction dot depth equal 5. So the model is created, a gradient boosted model with Bernoulli loss function. 500 iterations were performed. There were 41 predictors, of which 35 had non-zero influence. In the following code, we find the three most important variables according to boosting. The three most important variables according to boosting are, okay, so let S equal summary of R2, and summary of R2 gives us the predictors that are of higher value to the predictors that are of lower value. So the summary, we can see the importance by the relative influence. So SP MX BM, SP max L, and SP PCS ABP are on top, so they are of higher importance. The three most important variables according to boosting are SP max BM, SP max L, and SP pose ABP, and these are same as from the bagging method, where all the variables are used to perform to build random forest model, and where the square root of the number of all the predictors are used to create random forest model. SP max BM and SP max L variables are also chosen in that. So row names of S from 1 to 3 is SP max BM, SP max L, SP pose ABP. In the following code, we compute the training error of this boosting predictor, the train error. So let's look at that. Let pred.train equal pred, so we are predicting R2 on the train data. So predict of R2, comma, new data equal train, comma, type equal response. So we are using 500 trees, and head of pred.train is this. So convert the predicted values to class labels. So the predicted values are these. As you can see, they are in the decimal numbers. So predicted train data for more than 0.5, we add 1 to it. Head of y hat gives us this. Show working, head of s dot integer of trainnet class is this. To calculate the classification accuracy, we pass the command mean of s dot integer of trainnet class not equal to y hat, and that is 0. So the train error is 0. In the following code, we compute the test error of this boosting predictor. The test error is non-zero and are more than the test errors from the bagging method and random forest method. Let's have a look. Let pred.test equal predict bracket R2, comma, new data equal test, comma, type equal response. Using 500 trees, head of pred.test gives us this. Convert the predicted values to class labels. Let y hat equal pred.test. If it is greater than 0.5, then we add 1. Head of y hat is this. Misclassification, classification accuracy is found by passing mean of has.integer of tested class not equal to y hat, and that is 0.1100569. As we can see, this value is slightly higher than the error from boosting method and using and the randomly chosen square root of number of predictors. Do you think boosting helps prediction here? The boosting method helps prediction but is not better than begging and the square root of the number of the random forest method using the square root of number of predictors. As the computed misclassification test error is slightly more than compared to the misclassification error rate from the two other methods. For this dataset, boosting may have the overfitting problem. Boosting allows fitting a primary model to residuals repeatedly by allowing more influence given to observations in the next iteration where the fitting was bad in the previous iteration. The model gets boosted next time on the less influenced observation.